Hi everyone. I'm Nicholas, and today we'll talk about how and why confounding can occur in epidemiological studies and how we can deal with it. Let's analyze the association between the development of white hair and death. Initially, we observe a strong association between these variables. However, it is important to question whether having white hair directly leads to death. It appears that there may be another variable that is associated with both having white hair and death, namely age. As individuals age, the likelihood of developing white hair increases, as does the risk of death. Consequently, age confounds the association between the exposure of interest, white hair, and the outcome death. This confounding arises due to an imbalance between individuals exposed and unexposed to white hair concerning age, with age being strongly associated with death. Thus, it becomes evident that the association between white hair and death is primarily driven by age. This highlights the interconnected nature of variables in our study. They are not isolated, but rather associated with other variables that act as independent risk factors. This issue is particularly relevant in observational studies, as participants are not randomized to the exposure of interest, as seen in intervention studies. Let's see a hypothetical example. In this population, there will be some participants with white hair who are older, and there will be other participants who don't have white hair and are younger. Also, older people with white hair will tend to have more comorbidities, and maybe they have a lower socioeconomical status, which is reciprocally associated with less education, and they tend to smoke more, and maybe they have less access to the health system. The final consequence for these individuals is that they are at increased risk of death. On the other hand, younger people without white hair will tend to have fewer comorbidities, maybe a higher socioeconomical status, with more education and less smoking, and more access to the health system. They will tend to have a lower mortality risk. Confounding variables can introduce distortions in the relationship between the exposure and the outcome of interest. This occurs when the confounder distribution is unevenly balanced between the exposed and unexposed groups, resulting in an imbalanced confounder distribution. In our example, individuals with white hair have a higher prevalence of the confounding variable, indicating that they are generally older than those without white hair. The confounder serves as an alternative explanation for the observed effect of the exposure on the outcome. It can either completely or partially account for the relationship between the exposure of interest and the outcome. We will talk later about how we determine the extent to which the confounder explains this relationship. In our example, age acts as an independent risk factor for death, which confounds the association between white hair and death. This means that the effect of the confounder on the outcome becomes intertwined with when designing our epidemiological study, it is crucial to consider potential confounding variables. Collecting data on these variables allows us to adjust for them during the analysis stage. Failing to account for confounders can result in residual confounding, leading to inaccurate or erroneous results. Confounding can be classified into different types. Partial confounding occurs when the measure of association, such as the odds ratio, changes but does not reach the null value of 1. Conversely, complete confounding happens when the measure of association decreases or increases to the null value of 1 after adjusting for confounders. Positive confounding occurs when the measure of association decreases in magnitude after adjusting for confounders. For instance, it may change from 3 to 1, 3 to 2, or 0.5 to 1. Conversely, a negative confounder will increase in magnitude the measure of association after adjustment. For example, it may change from 1 to 3 or from 1 to 0.5 respectively. And how do we deal with confounding in epidemiological studies? In the design stage, we could perform randomization. This won't be the case for observational studies. Randomization is a powerful design technique that helps adjust for both known and unknown confounding variables. Restriction involves limiting the study population to a specific subgroup that eliminates or minimizes the influence of confounding variables. While restriction can provide strong control over confounders, it may come at the cost of reduced external validity and statistical power due to the narrower scope of the study population. Matching refers to selecting participants in such a way that they are similar to specific confounding variables. Enrolling participants who match relevant characteristics can be challenging, and analyzing the matching variable becomes more complex. In multivariate analysis, regression can be used to adjust for multiple confounding variables simultaneously. Always consider potential confounders in the design stage. Confounding is a major concern in observational studies, where researchers cannot control the exposure assignment. In such studies, it is essential to identify and address potential confounders to ensure the validity of the study finding. Failure to account for confounding can lead to misleading or incorrect results, as the observed association between the exposure and outcome may be distorted or exaggerated due to the influence of confounders. Neglecting to address confounding in a study can have serious consequences. The presence of confounders can undermine the internal validity of the study, making it difficult to draw accurate conclusions about the true relationship between the exposure and the outcome. Without adjusting for confounders, the study results may not accurately reflect the causal effect of the exposure, as confounders may introduce bias and confound the observed association.